All right, today we're going to take everything that we've learned about trigonometry and we're going to apply it to some real world problems. What we want to do is we want to take these words and we want to convert them into the triangles that we're familiar with. So a couple vocabulary words you need to know is angle of elevation and angle of depression. So right here, this is a good picture that shows what an angle of depression is. An angle of depression is from the horizontal looking down, and an angle of elevation is from the horizontal looking up. Now what's important about that is that horizontal lines are parallel. Okay, so horizontal lines are always parallel. Every horizontal line is parallel. But what that means is that those are alternate interior angles. And if lines are parallel, then alternate interior angles are congruent. What that means is that there is no difference between the angle of elevation and the angle of depression. And the reason that you can do that is you can look at it like this, at these two triangles. You can look at this triangle here, and then this one has been flipped over, but they represent the same thing. If you make this into a rectangle, this distance is the same as this distance, these two are the same heights, and then these angles are the same. So in the end, you can draw your triangle however you want it, but to locate your angle of depression and your angle of elevation, you're always going to put it off of the horizontal. Now, the biggest mistake that people make is in particular when the person or object that is looking is up. Everybody always wants to put it here. This is where they want to put the angle of depression, and it isn't where it goes. They want to put the angle of depression here. You do not ever put the angle of depression there. The angle of depression and the angle of elevation are the same thing. They are interchangeable, and it will always go right there off of the horizontal. This line is off the vertical. We want it to go off the horizontal. So let's translate these words into some pictures so that we can solve the problems. So the length of a tree's shadow is 13 meters. The angle of elevation of the sun is 37 degrees. What is the height of the tree? So imagine that you're standing to the side and you look over and you see a tree. So here's my tree, and obviously we have the ground. That's our horizontal line. It says that the length of the tree's shadow, it is important that you recognize that shadows always go on the ground. So the tree's shadow is here on the ground, and it is 13 meters long. The angle of elevation to the sun, so we've got our sun up here behind the tree, right? So it is casting its shadow, it's casting its rays on the tree, and then the tree is casting the shadow. So what happens is it creates this triangle right here. We're hoping the tree is standing up at a right angle. We're going to make that assumption. So we have 13 meter shadow. We have that the angle of elevation, so from the horizontal up, so from here up, is 37 degrees. What is the height of the tree? So we put our H right there. So if we go back to what we have been doing this entire unit, first thing we label our sides. So the height, according to the 37-degree angle, is the opposite side, and the 13 is the adjacent side. So we're going to take this and we're going to set it up. So what do we need to use? We need to use O and A. So O and A, remember we use our acronym SO, CA, TOA to remind us how to set it up. So O and A is tangent. So I set it up. The tangent of the angle 37 is equal to the opposite side H divided by the adjacent side 13. So you can think about this like a similar or proportions like we did with similar triangles, where you can cross multiply, or you can think about it like this. This is divided by 13. I need to inverse that, so I would multiply both sides by 13 and multiply this side by 13. So H is equal to 13 times the tangent of 37. 13 times the tangent of 37. Make sure your calculator's in degrees and hit enter. And we find out that the tree is about 9.8 feet tall. And we will tell you, or excuse me, not feet, meters. So about 3 times higher than that in feet. So 9.8 meters. We'll tell you what you want to round to when you're doing your homework and your assessments. Okay, this picture is kind of hard to see, but you can see a lighthouse and some stormy waters, and then there's a ship over here. An observer in a lighthouse 225 feet above sea level. So the observer is up on the top of the lighthouse. He's 225 feet above sea level, spots a ship on the harbor. So imagine his laser beam eyeballs going down here and they see the ship. The angle of depression from the observer to the ship is 48 degrees. Now here's where you're going to get tripped up because of the way that I drew the triangle. If you need to, flip that triangle over and imagine his eyeballs up there and they look down, right? But I think that upside down triangle, this doesn't make as much sense as this one. But remember that the angle of depression, the angle of elevation are the same. Find that horizontal line, draw that in, and put that angle. It is 48 degrees because the captain on the ship looking up at the top of the lighthouse is looking at the same angle as the observer in the lighthouse is looking down at the ship. They're both looking at a 48-degree angle. How far is the ship from the shore? So this is what we want to know, that horizontal distance. How far is that until he's going to crash into the shore? So you look at this, again, we're going to label our sides from the 48 degrees. The 225 is opposite. The x is adjacent. O and A means your use tangent. So the tangent of the angle, 48, is equal to the opposite side, 225, divided by the adjacent side, which is x. So if you go back to the same math that we did here, now we've been doing this for a while, multiply both sides by x, you get x times the tangent of 48. Remember, that's all a number. That all goes together. You can't separate it. Is equal to 225. Divide both sides by the tangent of 48. It all goes together as one piece, just like you would do if that was a 2x. You would divide. So you would type in 225 divided by the tangent of 48. And hopefully you have found a way for you to remember whether you're supposed to multiply or divide or inverse. X is equal to 202.6 feet. So the ship is 202, almost 203 feet away from the shore. Number 3, a ladder leaning against the wall. And in your mind, envision this. You're standing to the side and you see a ladder leaning against the wall. So here's my wall. I have a ladder leaning against the wall. The ladder and the wall both end at the floor. So here's my floor. All right, here's your ladder if you need to see it. Makes an angle of 74. The ladder makes an angle of 74 degrees with the ground. So here's your ground, and we make a 74-degree angle of elevation. If the foot of the ladder means the bottom of the ladder, is 6.5 feet from the wall, how high up the wall will the ladder reach? So that's x. Then it also asks how long is the ladder. So let's find length also. We're going to start by finding h. We can only find one at a time. So we're going to do, this is opposite and this is adjacent. And then when we get to it, we'll need to use that the length is on the hypotenuse. The ladder is the hypotenuse. In order to find the height of the ladder, we have O and A, so we use tangent. The tangent of the angle is equal to the opposite side divided by the adjacent side. So you would type in 6.5 times the tangent of 74. So think about it, that's a pretty steep incline, so it should reach up pretty high. So 22.7 feet. So the height of the ladder is 22.7 feet. So that's how high it will reach. Hopefully it will get into whatever you're trying, the eaves, so you can put up lights, or into the window for a fireman. And then you want to know how long the ladder is. Well, the ladder is going to be longer than that. It has to be longer so that you can lean it against there. But the ladder is h, and we want to use a. You can certainly use the height of the ladder, but you just found it, and you see how many decimals are involved. When you have to round, it's going to affect your end result. So we're going to go back to what we had originally, 6.5. We're not going to use the answer we just found unless we absolutely have to. So we have a and h, that's cosine. The cosine of the angle is equal to 6.5 divided by the length of the ladder. And this is a division problem. If you need to, put it over 1 so that you can see that proportion and cross multiplication. So we're going to take 6.5 and divide it by 6.5 divided by the cosine of 74, and you get 23.58. So the length of the ladder is 23.6 feet. So it actually probably in all likelihood looks a little more like that, like a steeper ladder. So it's reaching up pretty high because it's not too much longer than it was reaching up the height. Okay? So every problem, you're just going to translate it into a picture, and then you can solve the picture just like we've been doing this entire unit. A plane is flying at an altitude of 10,000 feet. If the airport is 112 miles ahead, what is the angle of depression from the plane to the airport? So this one's a little tricky because you have to decide where the 112 is being measured, and I'm going to measure it off of the ground because you wouldn't measure that diagonal distance unless you asked like how far is the plane actually traveling through the air. So I'm going to put the 112 on the ground. Now one of the problems is this is 112 miles and this is feet. Well, there are 5,280 feet in every mile. Okay, so 112 miles is 591,360 feet. So we have 591,360 feet to travel on the ground. The plane is flying at an altitude of 10,000 feet. And the question is asking, what is the angle of depression? So basically think about the pilot is up in the air and he's looking down at the airport. What is the angle that he's looking down at? Well, the angle that he's looking down at is the same as the angle as the air controller is looking up at him off the horizontal. Find that horizontal line and put your angle there. That's where your angle of depression and your angle of elevation go. This is the opposite side. This is the adjacent side. The tangent of the angle theta is equal to the opposite side divided by the adjacent side. So that's an inverse, so you need to find the inverse tangent. So inverse tangent, so theta is equal to the inverse tangent of 10,000 divided by 591,360. And you get that theta is about 1 degree. So he's a pretty far ways off. He's not looking very far. He's looking just basically just a little less than just barely under horizontal. Okay, a kite flying on approximately 100 feet of string makes an angle of elevation of 40 degrees with the ground. How high above the ground is the kite if you are holding the spool 2.5 feet above the ground and the string is straight? Now this one's a little bit tricky as far as your picture goes. Okay, imagine that you're holding your string right here, and your kite, this is, or you're holding your spool, right? And your kite is up here flying, and then it is above the ground. But you have this horizontal line right here because we have to do it off the horizontal. So I've told you that the spool is 2.5 feet off the ground. So it's 2.5 feet here, it's 2.5 feet here. The string, there's 100 feet of string, so that's where your 100 feet of string is. You don't fly a kite directly over your head, and you certainly don't fly it on the ground. So your string goes off at a diagonal, and it goes at an angle of elevation of 40 degrees. Find your horizontal and put your angle there. So what you're going to find is you're going to find x. X is from here to here. It's how high above the spool it is. Solve the problem the same as you always have. The side you want is opposite. The side you have is the hypotenuse, so that's sine. The sine of the angle is equal to the opposite side divided by the hypotenuse. Multiply both sides by 100, so you would say 100 times the sine of 40, and you would get that The kite is 64.3 feet off the ground. No, I say that. No, it's not off the ground. It's off the spool. So 64.3 feet above the spool. That's what this distance is right here. You have to add the extra 2.5 feet to see that it is 66.8 feet above the ground. If I don't specify, especially when you have things flying, if I don't specify how high above the ground it is, you're going to assume that it's attached to the ground, and you would just ignore this 2.5 feet. Because there's not a big difference between 64.3 and 66.8. So if I don't tell you what that height above the ground is, then you would ignore that. Really good application question right here. The Uniform Federal Accessibility Standards specify that the ramp angle used for a wheelchair ramp must be less than or equal to 4.78 degrees. The length of one ramp is 16 feet. The vertical rise is 1.5 feet. Find the angle of the ramp to the nearest hundredth. Does this ramp meet the UFA standards? And if not, what would you do to fix the problem? So I've given you a picture, and I really like the picture here because I want you to see where the ramp really is. Students always struggle with when I tell you that the length of the ramp is 16 feet. Students always want to put the 16 feet here, but that's not the ramp. Okay, the ramps don't lay on the ground. That doesn't do any good. So we need that ramp to go right here to actually be a ramp to take you from the ground up high. And then the vertical change is 1.5 feet. So let's check to see. What I want to know is this angle of elevation less than or equal to 4.78 degrees? This is opposite side. This is hypotenuse. So the sine of the angle is equal to the opposite side divided by the hypotenuse. That's an inverse. So we type in the inverse sine of 1.5 divided by 16. That's 5.37 or 5.38. So the angle in question is 5.38. So how can you fix the problem? Because obviously it's too steep. And that would make it difficult for for someone in a chair to be able to manually move it up the ramp. So how could you fix it? So in real life, there are a couple of things that could happen. You can't change that 1.5 feet. That platform or that ground where you need to go is 1.5 feet high. So you have a couple of options. If you shorten the ramp, then it's going to become steeper. So you can't do a shorter ramp. You would need to do a longer ramp. Now, in real life, a ramp can only go so far without supports, but you can do a long ramp. But there are limits to that too, because it can be very tiring to roll up a ramp like that. So it kind of depends on the length of that ramp, but as long as it's less than the 4.78. Now, another option would be to do it in smaller increments, to do a ramp and then a horizontal piece, and then another ramp, and still change that 1.5 feet. So you have several options for how you could fix that problem. Now these next two problems, these are going to be more challenging questions because there are multiple pieces that you're going to have to do. So let's look at how this is set up, and probably some of the hardest part is drawing the picture. A flagpole is at the top of the building, so envision that. 400 feet from the base of the building, the angle of elevation to the top of the pole is 22 degrees, and the angle of elevation to the bottom of the pole is 20 degrees. So imagine that there's a flagpole up on the school. So here's the school and here's the ground, and you have a flagpole up here. Okay, so we have our flagpole, and it says 400 feet from the base of the building. Here's the base of the building, and 400 feet from the base of the building, the angle of elevation to the top of the pole is 22 degrees. So this is 22 degrees. The angle of elevation to the bottom of the pole is 20 degrees. So this angle here is 20 degrees. And the question is, how high is the pole? What is the length of the pole? I just want that piece. Well, you can see there's what you want to do is you need to find the big triangle. So you would find this. So find the height of the building and the pole. and then find the height of the building. And when you find those two, then you would be able to find out the leftover height of the flagpole. So the way that that would work is from here to here is h. Let's find that first. So that's the opposite side, that's the adjacent, so we're going to use the tangent. The tangent of 22 is equal to the height of the building and the pole divided by 400. That's going to give you the height of both pieces. So 400 times the tangent of 22. And I'm just going to let that sit in my calculator. That is 161.6, but we don't want to round if we don't have to. So let's leave that number sitting there in our calculator. Then I'm going to find the height of just the building. The tangent of 20 is equal to, call that the right letter, x over 400. We're still standing the same distance away. Now we're doing the orange triangle. So you find out that x is 400 times the tangent of 20. So the height of the building is 145.6 feet. And basically what you want to do now is just subtract them. So always keep the decimals as far as you can. So we're going to subtract those two numbers. And we get that it is 16 feet tall. So the height of the flagpole, or the length of the flagpole, is 16 feet. Okay, so the tricky part is getting the picture, figuring out how to draw that picture, and then figuring out how to use it, because we're so used to just using a single triangle that we forget that we can use two. Okay, so number 8, last one. From the top of a lighthouse 1,000 feet above sea level, the angle of depression to a boat at point A is 29 degrees. 1 minute later, the boat is at point B at an angle of depression measuring 44 degrees. How far to the nearest foot has the boat traveled? So let's think about what we've got. We've got a lighthouse. It's 1,000 feet above sea level. The angle of depression, so it's looking out. We know that this is going to be some right triangles. So here's what we want to think about, though. The angle of depression to one point is 29 degrees. So we got 29 degrees or 29 degrees. Okay, 1 minute later, so here's the boat. 1 minute later, the boat is at point B. So let me call this something else. We'll call that A. Sorry, I called it B for boat. And the angle of depression measures 44 degrees. So let's think about whether the boat is getting closer or farther away. So if the boat were to go farther away, then you would have to look up a little bit more, and that angle would get smaller. So that means that the boat is coming towards the lighthouse, because now that angle is more, right? It's 44 degrees. Now again, that angle of depression is the same as the angle of elevation, so that's 44 degrees. So the question is, how far did the boat travel? I want to know this, but I don't have a way to find that. At least not yet. You don't have a way to find that. You could do that later with the law of sines and law of cosines, but we're not there yet, so we're going to use right triangles like we have been. So what you want to do is take this big triangle, find out this entire distance from the bottom of the lighthouse, and then use this smaller triangle right here and find this distance from the lighthouse, and the difference will give you how far the boat has traveled from A to B. So we set it up. I'll call this X, right? So this is opposite, this is adjacent, so that's tangent. So we take the tangent of 29 is equal to opposite over adjacent. So 1,000 divided by the tangent of 29. So it was originally 1,804 feet away. Okay, then now we need to do this smaller triangle. So we want to do this triangle right here, that little small triangle, find out how far away it is now. The tangent of 44 is equal to the same 1,000, because this is still the same height, that didn't change, divided by, let's call this y. So we have a different variable. Same math, doesn't change. 1,000 divided by the tangent of 44, and it is 1,035.5. Now it says to the nearer foot, but we don't round until the end. So I'm going to take this number here, and I'm going to subtract my previous answer, and I get that the distance is, or the length AB is 769, because it was 0.5, so 769 feet to the nearest foot away. That's how far it has traveled. That is this distance right here, 769 feet. That's how far the boat traveled in 1 minute. What you can do then is you can convert and see how fast it's traveling in feet per second or miles per hour. You can convert that into being able to calculate how long it will take until it gets to the bottom of the lighthouse or shore or whatever it is. You can calculate its speed that way. Every problem translates into a right triangle in some shape form. You may have to use two overlapping ones, but every problem translates into a right triangle. The horizontal is what determines your angle of elevation and your angle of depression. They are the same thing. They're both off of the horizontal. And so you can label it, draw your triangle however it makes sense in your vision, in your brain, and then label your sides, set up your equation, and solve it by multiplication, division, or an inverse.